additional work. Well, I guess most of you did assume that, but you must write it. Okay. Likewise, I could actually think of exchanging heat. So look at the topmost equation on the screen, and ds minus dq by t is greater than 0. I have made an assumption of constant volume. Let me make an assumption of constant pressure. No additional work. And without even going through the derivation and looking at these equations, okay, you can just tell me, that would be dqt, and dqt is nothing but dh. And if I do that, then I get TdS greater than or equal to dh. ds at constant pressure, that would be my conditions, right? ds at constant pressure, constant enthalpy is greater than or equal to 0. dH at constant pressure, constant entropy is less than or equal to 0. And exactly the identical arguments that I had a minute back. As in the case of internal energy, the same arguments hold true in the case of enthalpy, although enthalpy you'll find more often because you're working mostly at constant pressures. Now, let me try to get rid of this randomness from the system and see what happens. So, what is the term that is associated with randomness over here? This term. That's the heat absorbed, release, whatever. So, let me formulate two new functions, and one of them is A is equal to u minus Ts. So let's try to remove this randomness and see what the effect is. Let me formulate another one, which is H minus Ts. Okay. So, anybody who could tell me dA at constant volume, constant temperature, what would be the criteria for spontaneity? Less than or equal to 0. And dG would be at constant pressure, constant temperature, less than or equal to 0. Yeah, all you need to do is to use the previous equations. Here. So you could use TdS greater than du, and the other one I didn't write, TdS greater than or equal to dH. So these are the two that you'll need to use, and you get these criteria for spontaneity, right? Okay. So again, what is happening? What is happening over here is, let me write this, delta A is equal to delta U minus T delta S. This is what you will get finally, because you are at constant temperature, so S delta T would not be there. Delta G is equal to delta H minus T delta S. Now what is this? What exactly do these things mean? If this term, T delta S, is positive, which means delta S is positive, which means the entropy of the system is increased, then this is a negative term. And if delta A has to be less than 0, then the change of delta U would be positive as well. So I could have an increase in the energy of the system. An increase in the energy means that my heat is going into the system, and because the heat is going into the system, I could have more randomness in the system. Yes? On the other hand, if I have this as a negative term, right, then a lot more heat has to enter the system over here. Right? So if this is going to be a negative term, which means heat has to exit the system, a lot more heat has to exit, and the delta S of the surroundings would have to increase much more. Likewise, if you have, now this is something which you understand much more better. If you have an exothermic reaction, that is delta H is negative, that means heat is going out to the surroundings, then my system itself would go to a more ordered form. Delta S would be negative. Delta S is of the system, right? So it could go negative for an exothermic reaction. So, but remember, it cannot, the total thing cannot be positive. So it can only go as negative as much. This heat is given out. So some Q is given out Q at constant pressure, which is delta H. Whatever that heat is given out, that corresponds to certain amount of randomness in the system. So I can only go to a more ordered form in accordance with that heat. That Q has to be equal to TdS, not beyond that. Then delta G will be positive, it will not be a spontaneous reaction. The reverse reaction will be spontaneous. If it's an endothermic reaction, which means heat is taken up by the system, that increases the entropy of the system, which has to be a positive number, and more positive than whatever has done. So that is how you interpret these things over here. Okay, we have some more time. Now, this particular one, A actually stands for the German word called Arbeit, which means work. And it's also got a name called the Helmholtz free. And that's the Gibbs free energy. Was that free thing? Just now I told you that this is the amount of, for example, for an endothermic reaction, this is the amount of heat that's taken up. That's the amount of entropy that is changing. The rest of it is useful work. That's the free energy change. Yeah, delta G is not equal to 0. There's some heat that comes in, some of it that goes into randomness, the other is useful work. Now, the thing is that the maximum amount of useful work, maximum amount of work that can be gotten from one system is essentially delta A is equal to work maximum, and that's very easy to prove. And the idea is that what you have over here is take the Clausius inequality and take the first law. Right? And then what this gives you is dq. So instead of dq, write du is less than TdS plus dW. Right? And what this gives you is that dW in turn would be greater than or equal to du minus TdS. Yes? Now, dW, I'm trying to extract work out of the system. So dW has to be a negative number. And I need a large negative number, right? So it says VW is greater than or equal to this. If it's greater than, then it's a smaller amount of load because it's a small negative number. If it's equal to, then that's the maximum amount.